Hi, this is Professor Fernandez, and in this video we are going to start Lesson 7. We're going to talk about the first module only in this video, and just one thing I'll mention quickly is that there's a lot of foundational content in this lesson. So in Module 1 we will talk about tangent planes and also linear approximations. Module 2 talks about gradients, and then Module 3 directional derivatives. And really all four of these concepts are foundational for what we will do later on in the course. This is a nice little motivation and also application of the content we'll discuss. Just very briefly here, the white curves that you see, these are the level curves of the atmospheric pressure function P, where x is latitude, y is longitude, or vice versa, doesn't really matter. Meteorologists use this to study wind. And why do they do that? Because whenever there is a difference in pressure, that creates a pressure gradient. So there's that word that I mentioned we will talk about in Module 2. And that pressure gradient in turn leads to a force, which causes wind gusts. That's what we feel as wind. So to a meteorologist who wants to, for example, forecast the risk of a tornado or study the movement of a hurricane, knowing something about the level curves of the pressure function and whether they are very close to each other, whether they are very far apart, tells you information about pressure changes and wind gusts down the road. So this application will recur in the practice problems where you will use what we learned in this module, Module 2 I should say, to say something about the gradients, something about the wind speed at these 3 points in this diagram. So let me go on to the first module. In this module, we're going to talk about tangent planes and linear approximations. First part we'll do is tangent planes, and within that, you will of course notice the word plane. So a quick reminder of what we know from the equation of a plane. So here is a plane, and here is a point P on the plane. Let's call the point x0, y0, z0. And then here's a normal vector n to the plane. So we long ago had realized, this might be lesson 3 or so, that the equation of a plane can be thought of in the following way. If I pick a point at P, if I know a point P like I do here, and then I situate the plane in the XYZ axes, and then I draw a vector from the origin to that point and call that R. I find another point on the plane, maybe over here, point Q. And then I draw a vector from the origin, well, let's call the original one R sub 0. And then I draw a vector from the origin to the point P and call that vector R. Then we know, based on our vector properties of subtraction, that this blue vector has the representation R minus R sub 0. That blue vector is the vector, the directed line segment between points P and Q, which are on the plane. So the blue vector itself is on the plane. And therefore the normal vector being normal to the plane, it makes a 90-degree angle with this vector PQ. So that all explains why I didn't write this last little thing here, because what goes here is 0, right? If this vector n really is orthogonal to this, where which is R minus R sub 0, then remember that what we talked about in I think it was lesson 2 or 3, that when two vectors are orthogonal, their dot product is 0. So all of that information hopefully has come back, and what I'm going to do now is use a very, very similar approach to talk about the tangent plane, a very special type of plane. So I'm going to erase the things that we don't need here and go back and put in the things that got erased in the process. So there we go. Okay, so how do we convert all of this to talking about the tangent plane? First thing I'm going to do is draw my representative surface in such a way that I can view this surface S in such a way that I can view this plane as a tangent plane for this surface. First, I'm going to give you some very quick intuition for the tangent plane before we go off and leverage what we did with planes to get us the equation of the tangent plane. The intuition is I want you to think of maybe, an orange. Here's my attempt at drawing an orange, not a perfect sphere. And then think of grabbing like a sheet of paper and just picking a point on the orange and just putting the sheet of paper tangent to that point, right? And you can do this at all, portions of the orange, right? You can make this sheet of paper tangent to the orange by just moving it around where it just barely touches the orange, but you keep the sheet of paper perfectly flat, not curved at all. So you should have some conception, even based off of this and my bad drawing, that if I have a surface in space, and I pick a point on that surface, that I can hopefully draw a flat two-dimensional, surface, a plane that is tangent to that surface. So that's what I'm trying to depict here with this red plane. The question now becomes, how do I find the equation for this plane? And we are driven in our quest to answer that by the actual equation of a plane that we derive there. We need two ingredients. We need a point on the surface, and we need a vector normal to the surface. And we want it to be a tangent plane, so long story short, we are going to find a way to relate n somehow to the derivatives of something, right? Because we are talking about tangent plane. Just like tangent line has a, derivative in it, f prime of a, for example, tangent plane should probably have a derivative somewhere. Okay, so let's get started. So the first thing I'm going to do, as I said earlier, is I am going to switch again to the vector valued function framework here. Let me lay down the preliminaries for that. So let's consider S, which is the surface, to be generated by capital F of x, y, z equals k. All right. So this is a tiny generalization that's going to come in very handy. We could, and often we do, think about z equals f of x, y, and then think about the graph of that as being our surface. But if we restrict ourselves to that in this attempt to derive the equation of a tangent plane, we are going to have a little bit of trouble, because a sphere, for example, can't be put in the form z equals f of x, y. I can put each of the hemispheres in that form, but I can't put the whole sphere. Yet, as my orange example tried to convince you, we can draw tangent planes to the sphere at any point we like. So, we should come up with a way to not restrict ourselves so early on in our derivation. And this is the way to do it. We're going to assume that the surface S can be viewed as the level curve of some three-variable function. That's effectively what this assumption means. And that, again, is going to help us to apply what we will derive in a minute to surfaces like spheres. Great. So now what do we do? So now comes the vector valued framework approach. So as before, I'm going to think about P, the point on the surface, as the endpoint of a vector, R. And I'm going to call that R of t sub 0. And then I'm going to think about a curve on the surface that is generated by this vector valued function. Here's R of some other time, maybe t sub 1. Here's R of some other time, maybe t sub 2. Okay, so I'm going to write some of this down. I'm going to say let, and I'm going to call this curve, this blue curve, C. So I'm going to say let C be the curve on S generated, on S, passing through the points P and parametrized by the vector valued function x of t, y of t, z of t. Okay, and I'm going to just point out, to be consistent with my figure here that I've drawn up at the top, note that at t sub 0, the vector is r of 0, y of 0, z of 0, matching our point up here. Okay, great. So since C is on S, and S is generated by this level curve of capital F, we know that F of the parametric representation of the points on the curve C, x of t, y of t, z of t, F of that equals K. This is just a mathematical expression that, I have a curve, a blue curve here, that is on the surface. So all of the points x, y, z on that curve satisfy this. Now, in this second step, I'm viewing every single point on the curve C parametrically as x of t, y of t, z of t. So put those two together and you get this result, that all those points viewed parametrically, when I evaluate f at those points, I get k. Just again, a representation mathematically that the curve is on the surface S. Okay, great. So what am I going to do now? I'm going to use the chain rule. Again, we had that intuition earlier that it's a tangent plane. Tangent, there should be some derivative somewhere. So now here's where we're going to start differentiating. To remind you what we did with the chain rule, I believe this was in the last lesson, lesson 6. F is a function of 3 variables, and each one of these is a function, single variable function of t. So if I want to differentiate with respect to t, which is what I'm going to do, that is the only variable, the implicit variable here, I have to pass through these partial derivatives first, because f depends on 3 variables. But then once I'm at each one of these variables, to get to t, it is a normal derivative, not a partial derivative, because they are single variable functions of t. So to write that out, I'm going to take, again, d by dt of this entire equation and use the chain rule on the left-hand side. That gets me partial f partial x dx dt plus partial f partial y dy dt plus partial f partial z dz dt. And then I have on the right-hand side derivative of a constant that is 0. So if you squint, you can see this as a dot product of a very interesting vector, the vector of derivatives of capital F, dot product with another interesting vector, the vector of derivatives of x, y, and z. And I'm going to write this one more time in a way that is going to make it even more suggestive. This is the dot product of this vector of derivatives of f with, let's go back up here and remember where x of t, y of t, z of t came from. It is the vector valued function r of t. So if I go over here and write out r prime of t, that is the vector valued function of derivatives. Remember, this is how we defined r prime of t when we talked about vector valued functions in a previous lesson. I can't remember at the moment what lesson that was. Maybe lesson 5 or 4. So this thing down here, actually I'm just going to write it that way instead of putting in that whole vector. I'm going to put it as r prime of t equals 0. Great, and we are so close. You can see here the blue box emerging with the definition of the tangent plane. So we're about to get there. So at this point, what do we know? Going back to our knowledge of dot products, which goes back to lesson 2. We now have 2 vectors, this one and that one, whose dot product is 0. Okay, so we know that these 2 vectors are orthogonal to each other. This vector is new. We don't quite know what to make of it just yet, but this vector, again, when we talked about vector valued functions, we know exactly what this is. This is the vector that points in the direction of the tangent vector to r. So now let's scroll back up to our figure and let me remove some of these things that we're not going to need anymore. So now that we've gotten to this point where we've got some information about a tangent vector, let's do one thing. Let's go back and apply this equation that we've just derived, which is true for every single t value. Let's now apply this to t equals t sub 0. In other words, let's look at just t sub 0 here. And I haven't been writing it for f, but you know, f ultimately depends on t through its dependency on x, y, and z, and their dependency on t. So I'm just gonna put evaluated at t0, right? To understand to mean that you plug in t0 here, you get an x, y, z, and then that generates a point, which is the point p, and you plug those x, y, z values into these derivatives. So now we are looking at this equation at t sub 0. And r prime of t sub 0, what is that? If I scroll up, well, you see this r right here, this was the vector going to point P. R prime of t sub 0 is now the tangent vector at P. And the whole idea that we started with was that this red tangent plane was the tangent plane at point P to the surface. And so now we have something very important. We have a vector that sits in that tangent plane, r prime of t sub 0. And we are in really good shape because all along we've been searching for a normal vector. We're very close. We have a vector, r prime of t sub 0, that is in that tangent plane. And this equation tells us that that vector is perpendicular to this thing. So our conclusion is that the normal vector that we've been searching for is this mysterious vector that has emerged. Because again, it is orthogonal, normal, to what we know is a vector on the tangent plane, r prime of t sub 0. So that is really cool. That gets us exactly what we want, because if we unravel this dot product here, what happens? Well, so I can actually calculate the dot product. And if I think of this r prime of t sub 0 vector, this one, as I did before when we talked about tangent planes, in the sense that, you know, this r prime of t sub 0 vector starts at P and it points in the direction of some other point on the plane, Q, and we redo everything that I did at the beginning of this video to get us to this as being the second vector that we're going to dot with the normal vector. Same exact reasoning applies, and I can then write this, which is our new normal vector, dot some points on the plane, x0, y0, z0, and then some other points, x, y, z, and their difference is a vector on the plane. The dot product of these two should be 0. So that gets me to, running out of space here, but I have space down here. That gets me to, multiplying things out, I get fx at the point x0, y0, z0 times x minus x0 plus fy at the point x0, y0, z0 times y minus y0. So I'm writing out this dot product up here. Plus fz at the point P times z minus z0 equals 0. That is the equation of our plane. And we have now derived it in, again, the general setting where the surface is viewed as the level curve of some capital F function of x, y, z. To get us then finally to this definition, now we are going to simplify to the case when z equals f of x, y. And how do we do that? This case is the same as capital F of x, y, z equals z minus little f of x, y, z equals 0. Okay, so what did I do? I subtracted the f of x, y to the other side. I called that capital F. And then, you know, of course, when I subtract this to the other side, I get z minus little f equals 0. So now I have capital F equals 0. This is my k value. This is my capital F function. And let's see what happens when I use that capital F function here. Well, let's calculate the partial derivatives. F sub x if this is my capital F function, is minus little f sub x. F sub y, if this is my capital F function, is minus little f sub y. And then f sub z, this is the only z here, is 1. So if I then use that in this equation of the tangent plane, this would become minus fx, this would become minus fy, and then this would become 1. Okay? And if I then move over this minus fy, y minus y naught, to the right-hand side of the equation, move over this to the right-hand side of the equation, I finally get this. So we are then at a point where we can go to this definition and understand all of the work that it took to get here. So what does the definition say? It says, suppose f is a function on some domain, and it has continuous partial derivatives on that domain. The tangent plane to the surface, z equals f of xy, at this point is exactly what is over here. Okay, so notice again that this is the equation of a plane. It has the form z minus z sub 0 equals a number x minus a plus a number y minus b. That was our equation for the tangent plane back from when we first talked about it. But, hopefully, and again, it might be a good idea to go back and review what we did to get here, because actually we have gotten to an equation for a tangent plane that works, and that was by design, for surfaces that are more general than z equals f of xy. Again, I can't put the sphere in this form. I get a plus or minus on the right-hand side. But I can find the equation of the tangent plane to a sphere using this other form. So we've gotten now to this point where we have the equation of the tangent plane. So now let me show you how you use this stuff in practice. We'll do an example. And then I'll show you also with the technology what this looks like and what the plane looks like. Okay, so here's the example. Find the tangent plane to z equals x squared plus y squared at this point. So now I know, I'm just going to write down that equation. This is of the form z equals f of x comma y. So I'm going to write down the equation of the tangent plane first, just so I know what I'm looking for. So z minus the function's value at ab. So z minus f of 1, 1 equals the partial derivative at that point times x minus the x value of the point plus partial derivative at that point times y minus the y value at that point. Okay, so you can see that there are three things for me to find here. I need to find this, this, and this. So one of these has already been found for me. They've given me that information right here. This is f of 1, 1. And we can just double check that because we have the equation, right? 1 squared plus 1 squared equals 2. So I'm going to update here my tangent plane equation. So I only have two things left to find. So, this is one of the nice things about doing lots and lots of work on the theory end to get the tangent plane equation. Once you get the tangent plane equation, actually finding the equation of the tangent plane is much less work. So I need to find the partial derivatives of f, and then I need to substitute in 1, 1. So looking back to the function up here, partial derivative with respect to x is 2x. And if I substitute 1, 1, I just get 2. Partial derivative with respect to y is 2y. Substitute 1, 1, I also get 2. So I'm just going to plop those numbers in here and write down the equation of my tangent line. There it is. And if I solve for z, this is what I get. Okay. Again, looks like, a perfectly normal equation of a plane. But what's so special here is that this is the equation of a tangent plane. So now, rather than me trying to draw this out, I'm going to show you with technology what this looks like. So I'm going to switch over here to look at the tangent plane, and then switch on my little cursor. So what have I done here? I have plotted the function itself down here, z equals x squared plus y squared. This is another paraboloid. So I'm just going to rotate things around a little bit so you can kind of get quickly acquainted paraboloid, the cross sections in the xz axis, in the xy axis. In the xy axis, you get circles, because if I set z equal to a number, you get x squared plus y squared equals a number. In the other cross sections, like for example the the xz plane, you see that's a parabola, because you would get z equals, if I set y equal to a number, you get z equals x squared plus, I don't know, 4, 9, 1. And those are parabolas. Okay, so this is a paraboloid. And then let's talk about its tangent plane at the point 1, 1, 2. So first I'm going to turn on the point 1, 1, 2. So you see there it is, it has appeared in red. And now I'm going to go over here and click this button to turn on the tangent plane. So there's the tangent plane. I'm going to change the colors to make it a little easier to see. So give me 1 second to do that. Let's change this to constant color and let's make it green. And then let's go over here and change the tangent plane to constant color, and let's leave that in red. Okay, so now I'm going to just pan around so you can see, this is really the equation of a plane. See how it's just, and it's a tangent plane. It is just barely touching the surface at the point 1, 1, 2. And this is, I have pre-programmed in here the equation of the plane that we found. So again, you can play around with this later on, and you can draw different surfaces and pan around to make sure, and this is a way to check your work. Notice, let's see if I go here and maybe I made an error in calculating, let's assume I made an error in calculating f sub y of 1, 1, and let's say I put a 3. That no longer looks like a tangent plane. Right, you can see that little bit of the plane up there, which actually slices through the surface. It's kind of hard to see because the error I put in here of a 3 is pretty close to 2. But, let's say I make a more egregious error and I make that 13. Then you can see that's not a tangent plane at the red point. Right, it's not tangent to the surface. So just by way of checking your work and also just exploring this concept, I highly recommend going to this applet and playing around with the tangent planes you get. You can go to the practice problems, and then the solutions are on our site. So let me go back to the files app and then talk about the next part of the lesson, linear approximations. Okay, so having just talked about tangent planes, if you think back to single variable calculus, when you got to the point where you knew how to write down the equation of the tangent line to a function y equals f of x at a point, let's say right here, you were able to write down the equation of the tangent line at that point. You saw pretty clearly that the values of the tangent line, the y values, were pretty close approximations to the values of the function, at least if you were near the point of tangency. Right over here, these values are not very close approximations to the values of the function. That's a big difference. But, right in this little vicinity of the point of tangency, they are pretty close. And then from there, you develop this notion of a linear approximation. That f of x is approximately f of a plus f prime of a times x minus a. And if you remember this far back, this was called L of x, the linearization of the function at x equals a. And this was called the linear approximation. So, the linearization, this is just the equation of the tangent line. The slope is f prime of a, that's the slope of the tangent line. And then the y-intercept, so to speak, is f of a. So this L of x is just the equation of the tangent line, but it's also called the linearization of the function at a. And then this was the linear approximation. So, written this way, we again get that intuition. The value of the function at x, here's the actual value of the function at this x value. The actual value of the function is approximately the value of the tangent line at x. And that's this point over here. So So here, this is L of x, the y value here, and this is the y value f of x. Okay, so we are going to just, generalize this using the exact same reasoning as before, as in the single variable case, to this multivariable context. And how do we do this? Well, we start from the equation, now we're passing formally to the multivariable context. We start from the equation of a tangent plane, the one that we just started working with. So that's this equation. Great. F of y of AB times y minus b. And then we are going to add f of AB to both sides, plus fx a minus b, x minus a, and then y minus b. And then just like before, if I just blotted out all of this, and I blotted out this b, and I blotted out this a, well, maybe not blot out all of it. Let's blot out this part, and this part. You can see that this already looks like what I just erased a minute ago. This already looks like f of a plus f prime of a, x minus a. So all that being said, what I'm going to do now is define our linearization function to be this entire right-hand side. Let's call this L of x comma y now, because there are two variables here. There's a y. And then what is going on then? This is, as we can clearly see, this equation is literally the equation of the tangent plane. That's how we got it a few minutes ago in the derivation. And z here is the z value on the tangent plane, just like x and y are, part of the point, x, y, z, points on the tangent line, on the tangent plane. But again, through our usual drawing, the multivariable version of the single variable tangent line that I just erased a minute ago, right? If this is the tangent plane with this equation, and if this is the surface, z equals f of x, y, then our conclusion is that if xy is close to AB, in other words, if you're like, in a little vicinity of the point of tangency, which is this red dot here, then the values of the function should be close to the values on the tangent line. Okay. So again, you can see that in blue, this is curving down away from the tangent plane, whereas the tangent plane is a plane, it continues going straight that way. So similar idea, if I wanted to evaluate the function at this specific point, right here on the function, I could approximate it with the value on the tangent plane. And of course I would incur some error, but that error is going to get smaller and smaller and smaller as I approach the point of tangency. At the point of tangency, by the way, f of AB is the value of the function. And if I plug in x equals a, y equals b into the tangent line, I also get f of AB. So again, this should match up with what we know from single variable calculus. And this leads to our definition down here. So effectively a direct generalization of the multivariable linearization technique, of the single variable linearization definition. Suppose f is a function with domain D, and that it has continuous partial derivatives. We call the function the same thing I just wrote up there, the linearization of f at AB. And if I approximate the value of the function at xy with the value of the linearization at xy, in other words, the point on the tangent plane, then this is called linear approximation or tangent plane approximation of the function at AB. Great. So let me show you an example of how that works. So consider again the same function from the previous example at the same points, and that should be a 7, example 7.1. So I'll fix that. And then number 1, find the linearization of f at 1, 1. Okay, great. So the linearization, remember, is just, if I scroll up here, like if you were to solve for z in the equation of the tangent plane, right? If you just solve for z, all this thing that you get on the right-hand side is the linearization, right? So that's how we define the linearization. So if I scroll up even further to where we had done our original example, there it is. We had already solved for z. So this thing is the linearization. That is L of x comma y. So I'm going to write it down here. That was 2 plus 2 times x minus 1 plus 2 times y minus 1. And then number 2, use your answer to approximate this value. Okay, well, so we said first that this is the linearization. This is the linearization at the point 1, 1. We are now trying to approximate the value of the function at the point 1.1, 1.1. So 1.1, 1.1 is pretty close to the point 1, 1. So we expect that the value of the function at this new point is approximately the value of the linearization at that point. Right? Geometrically speaking, the value of this function is a point on the surface, z equals f of xy. The value, this value is a point on the tangent plane to the surface z equals f of xy at the point 1, 1. So that's the geometry. Okay, so then I'm just going to basically write down, using this L of xy, what this L of 1.1, 1.1 is. This is 2 plus 2 times 1.1 minus 1 plus 2 times 1.1 minus 1. So I get 2 plus 0.2 plus 0.2. I get 2.42. Okay. It turns 2.4, sorry. I'm skipping ahead a little bit because it turns out that f of 1.1, 1.1 is exactly 2.42. So again, this gives you another good, example to help solidify these concepts. The function's value at a point that is near the point we calculated the tangent plane at is approximately the y value on the tangent plane, which is 2.4. And that's very close to the actual y value of 2.42. Great, so I'm going to attempt a 30-second summary of what we did in this lesson. And actually, the 30-second summary is possible because here is all of the work that it took us to do to get to the main concept, which is the equation of the tangent plane. And summarizing that is fairly simple. So, to reiterate, we actually derived a more general equation. You can, I believe you will explore this in the practice problems for finding the tangent plane to a surface. This equation works for examples for spheres, but the definition here is the simpler one that we use more often. So to find a tangent plane, you essentially, the vector n, the normal vector that you're using, is essentially x component is this, y component is this, and then z component, like we said over here, the z component fz is just 1. So this gives you that view of the tangent plane, and you can then have to you then have to go off and calculate the partial derivatives of little f of xy to get the actual numerical values of that normal vector. That's what we did here in an example. We calculated that, we calculated that. Sometimes you may have to calculate the f of ab value, or sometimes it may be given to you, like what happened here. Either way, right, that will eventually get you to the equation of the tangent plane. Once you have that, the practice problem you're working on may stop there, but you should also remember that when you solve for z in the equation of the tangent plane, the right-hand side is what we call the linearization. And that is, again, another way to view the actual tangent plane itself. And therefore, if you are close to the point of tangency, 1 comma 1 in this case, then the values of the function will be approximately the values on the tangent plane near the point of tangency. And if you use this to estimate little f of x comma y, then that's what we refer to as linear approximation or tangent plane approximation. Great, so that's it for this video, and I'll see you in the next one.